To go ahead without you necessarily seeing my smiling face, but it is indeed, well, except for technical difficulties, it's otherwise smiling. So, hello and welcome to Saturday at Hack the Sea. So let me get around to my PowerPoint presentation here, and let me just basically go through this, and I've got some other things to show you. So I'm going to talk today about some work that I'm doing on something called protected AIS. And I'll just quickly give you a little bit of an overview of what I'm working on and what the problem is and what quasi solution I worked on. So automatic identification system is the system used by vessels at sea for situational awareness. We'll see some examples of this coming up in a minute. But obviously, this is the way ships let each other know where they are and what kind of ship they are and those kind of things. And as we've discussed, and certainly part of the talk yesterday, but and you may know from other sources, AIS suffers from a number of security vulnerabilities. And so because of those vulnerabilities, it makes it prone to some spoofing type attacks, replay type attacks, and things like that. And so basically, a bad guy can send bogus messages. So I came up with a proof of concept that uses some public key cryptography methods and provides something that I call protected AIS. And it addresses some of the vulnerabilities, but one of the keys that I also wanted to be able to employ was that whatever solution I designed needed to be backward compatible with the existing protocols, or else it really wouldn't be very much of a demonstration of capability. So here are acronyms and abbreviations. So again, for those of you who didn't sit in yesterday, a quick 2-minute overview. AIS, as I said, it's a situational awareness system used between vessels and ground stations so that vessel traffic management systems know where vessels are that are in their area of responsibility. Maritime administrations know about vessels in their AOR. Ports can keep track, things like that. But also equally, and possibly even more importantly, vessels can keep track of other vessels with whom they are in proximity. And they can get some idea from those other vessels what type of vessel they're looking at, possibly information about their cargo, the size of the vessel, speed, course, bearing, rate of turn, current position, destination, all that kind of stuff. And there are a class of vessels, mostly big ones, that are required to transmit AIS information. And for the work that I'm doing, this is important because there's 2 different types of AIS position information broadcasts, Class A and Class B. The vessels listed here, the big vessels, are the ones that are required to transmit Class A. And Class A really gives more information than Class B. Actually, for some of the work I was doing, I needed to know stuff like rate of turn, and Class B didn't say that. But Class A and Class B gives me sufficient information about vessels. Warships are exempted from being required to use AIS. So warships can transmit AIS, but they are not required to. So here's an example of an ECDIS display. I'm going to try actually another display. Let's hope I have the right screen up. I don't. This is a display coming from the feed that I have at Embry-Riddle Aeronautical University in Daytona Beach. And so you can see right now, here's the university. We can see right now about 10 vessels. A second ago, we could see 11. Anyway, and the furthest vessel we can see is only actually about 14 kilometers away. But if I mouse over, it tells me that there's that vessel there. But if I click on it, I can actually get a lot more information. So this is a pleasure craft. You can see it's only about a 33-footer. Right now it's offshore a little bit in Daytona, but you can get an idea of where it's located, when we last saw it, course, heading, speed, latitude and longitude. Tells us that it last saw us a minute ago. And we're getting everything here from terrestrial AIS as opposed to satellite. And the name of this boat is Fish Izzle. So anyway, Here's the other vessel I was saying that for some reason just disappeared for a moment. Give it a second, it'll come up, hopefully. Okay, this is something called the Janus. This is a sailing vessel, sailboat. And again, we can get additional information. Note in this case, we can find out it's from Fort Lauderdale. They may not have programmed in what their destination is, but sometimes, we will get that information as well. And then I've spent a lot of time in the last day talking to you about OpenCPN. And OpenCPN, again, here's the fishizzle. That other boat may be right around in here. I've been losing boats underneath that marker. Let me just go back here. Okay. Anyway, so like I said, this is an example of what you see on an ECDIS display. There are a variety of other applications you can use. This is FindShip. It's a mobile app that I have on my phone. I'm getting AIS information from here as well. I can use a web browser application. This is, again, from FindShip. And, again, you look up a boat by name or MMSI or IMO number, and you can, find out where they are. Now, the AIS Communication Protocol, largely, it's defined in a couple of International Telecommunication Union recommendations. And generally for radio, it employs this self-organized time division multiple access scheme. And so basically, each vessel is finding its slot and is transmitting during its slot. Slot times are pretty short. And during its slot transmissions, it can also reserve other slots that it wants to use that are presumably haven't already been reserved by other boats. Now, I told you that, again, just to give a real brief high-level overview of what matters for AIS as far as my little project here is concerned. The other thing that my project obviously needed was some encryption. And so here, real quick, we have 3 different types of crypto functions, and I'm classifying them in a pretty standard way based upon the number of keys that they use. So a hash function doesn't really have a key. It's one-way encryption. And it's used for message integrity. Secret key cryptography uses a single key for both encryption and decryption. And we largely use secret key crypto for privacy and confidentiality. The stuff that I'm working on, I have no desire to keep private or confidential, so I don't even really use any secret key crypto. And then public key crypto, which is really the most interesting out of this. We've got two keys. One key is used for encryption. The other key is used for decryption. And the keys are mathematically related, but of course, knowledge of one key doesn't yield knowledge of another key. So therefore, what we can do is we can keep one key a secret, but my own personal secret, my private key, and then the other key I can put out there for the rest of the world to use. Public key crypto generally used for authentication as well as non-repudiation and secret key exchange. For purposes of my work, all I really care about is message integrity and sender authentication. So we'll see a little bit more with hashes or something like that, and a little bit more with public key crypto. So again, hash functions and checksums, for that matter, cyclic redundancy checks, do the same thing. Basically, these are just mathematical formulas that provide you with the digital fingerprint, if you will, of any sort of binary string. It can be a message, a file, a frame in the terms of, like a data link layer transmission, a message, packet, segment, whatever you want to call it. The cool part about hash functions, and again, checksums as well, is that a particularly sized checksum, like a CRC16 or an MD5, is going to give you the same size hash value or checksum value regardless of the size of the input. So if you're using MD5, you're going to get a 128-bit output. Use a CRC16, you're going to get a 16-bit output. The value of your checksum or your hash makes it impossible to determine what was the length of the original message, and certainly makes it impossible to figure out the contents of the original message. So that's, of course, why they always call these things one-way encryption. Now, public key crypto, of course, is a tad more complicated, but as I suggested before, I can keep one of the keys, my own closely held secret. So again, that's my private key. The other key I can post anywhere I want. So for example, on my website, I have posted my public GPG key. I also have it posted at multiple key servers. And so the idea is this. If I've got two parties to a communication, Alice and Bob, we always have Alice and Bob. If Alice uses Bob's public key to encrypt a message and send it to Bob, Bob presumably is the only one that can decrypt the message by using his own private key. So that's one way of having secure communication from Alice to Bob. Now, if Alice encrypts a message with her own private key, anybody who can get to her public key could decrypt it. But what that does is it proves that Alice is the only one who could have sent it. So despite the little typo that I have here, that method can be used to authenticate Alice as the sender. And if you like pictures, I know these look like Lois and Clark, but that's supposed to be Alice and Bob. So presumably everybody has their own private keychain. And in their private keychain, they have their private keys. Now, they can also have a public keychain, and there may be a shared database of public keychains, and that's really the direction I want to go in. But again, this page sort of replicates what I said on the previous page. If Alice sends a message encrypted with her own private key, Bob can decrypt it using her public key, and he can get the public key from the database. And again, that authenticates Alice as the sender. If she wants to send a message to Bob, she can use that same database to get Bob's public key, send it to Bob. Bob's the only one who can decrypt it. And again, that's where I get my private, that's one way of getting privacy. Although typically we don't use public key cryptography for, that kind of communication. Now, I told you all of that so I can tell you this. Here's my problem statement. AIS, as we've described before, has a number of security weaknesses. One of them is there's no geographic validity check for the sender. There is no timing check on when the message was sent. There's no authentication of who the sender actually was, and there's no message integrity check. So in fact, there's no way to prove that the message that you received is the message that I sent. Now, there are a number of issues that this brings up. Obviously, I can spoof messages, make bogus vessels if I want. I showed an example yesterday of making virtual ATONs that were bogus. I can also send out false SOS messages via AIS. I can send out closest point of approach messages that are fake weather reports, all that kind of stuff. So this page is also another way of looking at this is all the message pathways from vessel to vessel or to AIS gateways, vessel traffic management, that kind of stuff. And the two hooded fellows there on the chart are supposed to represent bad guys, and this is merely showing different attack vectors. So if you're attacking a vessel or in some cases, some of the landshore facilities as well, you can do this via radio. In some cases, you can also attack the system using software-based threats just via the internet. And actually, for my purposes, it doesn't really matter what your vector is. The National Marine Electronics Association, NMEA, is one of the organizations that standardizes what these messages look like, and is certainly the go-to place internationally for connecting devices to each other on board vessels. A lot of the NMEA work has gone forward as International Organization for Standardization, ISO work. But in any case, the NMEA 0183 specification which has been around now for about 35 years, is probably the most commonly used over the air because that's what the ITU is using. There is, of course, a significant embedded base of 183 equipment, particularly on large ships. And there are newer standards, NMEA 2000 and OneNet, which is coming out sometime this year. Right now, they're not used so much over the air. They're used within a vessel. And NMEA 2000 actually is used quite a lot on recreational vessels or personally owned vessels, much more than it is in the commercial world. Now, I told you all of that so I could show you, I want to show you what an AIS message actually looks like, because that's important to the protocol work that I did. And again, if I go back here to OpenCPN, this isn't interesting. There's Fishizzle again. I'm going to go right here because unfortunately it's a class B, so it's not telling me my rate of turn. But you can see here, this is its course, 172. Its course is 172. Its heading is 217 degrees. I would be very interested in knowing its rate of turn right now, particularly since it's been a couple minutes since we heard from them. But in any case, if I go up here and I show my NMEA debug window, I can see the messages that are coming out over the air. And actually, I normally can. I'm not sure why I am not now. Well, again, the hazards of doing a live demonstration. Okay, well, I'll come back. We'll have some data in here later, I hope. But in any case, this is what the messages look like. So let me try to interpret a little bit what you're looking at here. So a 0183 AIS sentence has, for purposes of my discussions, it has a header. And in the header, there is a prefix. There is an identifier of what type of device you are looking at. And then there's some sequencing information, if it's AIS, and a channel number so you know what channel the transmission is on. Then you have the content. The content in AIS, it's called an encapsulated payload. And we'll talk a little bit about that. And then there's a trailer. And the trailer mainly has information telling me how many padding bits am I going to have to make sure that I have 6-bit alignment, and what is the checksum for this particular transmission. Not the message as a whole, but the individual transmission. And the padding bits and the checksum just covers the content area. So put another way, here is a standard AIS message. So, for example, the exclamation point at the beginning says, this is an NMEA formatted message and it has special encapsulation. So for example, if you look at a GPS message, GPS messages start, I think, with a $sign. That just indicates, yeah, this is an NMEA formatted message, but there's nothing special about the format. You can basically just read everything. You don't have to translate it to a different format. The next field, the AIVDM, identifies the talker ID, that's the device. In this case, AI means AIS. And then the encapsulation format is identified in the next 3 characters. That's the VDM. In this case, VDM stands for VHF data link message. That means it's a message coming from another source. Now, the transmission that I'm showing you here is referred to as a sentence. A message may be composed or will be composed of 1 or more sentences, usually never more than 5 sentences. But in any case, the first number here tells me how many sentences are required to fully compose this message. In this case, there's only 1 sentence. The next number is the sentence or the fragment number of the message. Now, in this case, there's only 1 sentence, so this is going to be sentence number 1. But as you can imagine, if the number of sentences, say, were 3, well, then I'm going to have a sentence number 1, 2, and 3. But how do I reassemble that? Well, that's the next field, which is usually null when you only have a one sentence message, but it's a serial number. So you could use pretty much any number you want here. This provides for the reassembly of the fragments. So if I had that message I just mentioned, a three-sentence message, let's say it's got serial number 7, I would have something here that would be a 317, 327, 337. The next identifier is going to be an A or a B. It tells me which channel number, which frequency I'm using for AIS. Then I actually have the content. I'm not going to get into what the encapsulated payload looks like, but it's in something called armored ASCII, and everything's put into 6-bit bytes. Then I have a number telling me what is the number of padding bits that I need to add to get 6-bit alignment for my content. And then lastly, I have a checksum. The checksum is actually a pretty naive checksum. It basically is nothing more than an exclusive OR of everything in the content field. Now, I told you that so I can tell you this. Some of the tools that I've mentioned, one of the tools I have allows me to create any pretty much AIS message I want. I can create most messages. There are some message types I actually just have not built in yet, largely because they're not commonly used and largely because I just haven't added them yet. But if I go around here, so here's this menu program that I have. So for example, let's say I want to create a type 1 message. A type 1 message, as you can see there, is a position report, class A position report. So there we go. It wants to know the talker ID. I can choose all sorts of different talker IDs. And in this case, I'm just going to accept the defaults because I want an AIVDM message. And then I need to have an MMSI. That's the Maritime Mobile Service Identifier. And actually, for purposes of what I'm doing, you can choose any 9-digit number you want. For the protected part, you have to choose ones for which there are key pairs. And I'm just going to take all the defaults here, with the exception of when I get to my latitude and longitude. My latitude, I'm going to put at 29.1 because I want it to match the example in the book. The longitude is -80, 080. This is actually off the coast of Daytona Beach. I'm not going to use protected mode for this. And I'm just going to let this go out channel A. And I get a message that looks like this. Now, what this allows me to do is I could then copy this and paste it as a command, and it will now create for me the message that I want. Now, you can actually batch all this together so that you don't have to, do this all stepwise. But when I just ran that command, the PAIS_ping command, it then created, the binary of the encapsulated payload. Anyway, that's what I'm showing here. So I ran that ping command, then I ran the other command that gives me the encapsulated payload. And now I can run another program called AIS NMEA, and it now creates for me an AIS message. And so from here, I can either transmit this, I can put it into a file with some timestamps, and I can make things happen. Some of you, if you heard me talk yesterday and you saw that I created some virtual ATONs, well, basically what I did is I determined what's the latitude and longitude of where I wanted the ATON to be, what type of ATON did I want it to be, and I just created a bunch of these messages, put them in a file, and just sent it up to OpenCPN so that they would appear. Now, once I've created the message, I need to be able to parse it. So here again is the AIS message right there. And so this parser shows basically, obviously parsing it, telling me what the talker ID is, verifying the checksum, and then showing me what all the contents were. And you'll notice the only contents of real interest, well, it's a message type 1. That's the we put in. There's the latitude and the longitude. And again, if you wanted, you could take that URL and look it up in Google Maps or something like that. But in any case, that's the tool that I have. Now, where I'm going with this is this. I could take that same message. I could go to a public AIS message parser, like I've done here at AGG Soft. put in the message, decode it, and it tells me all the stuff that's there. One thing I would like you to notice is it is telling me that it is showing all 26 of 26 entries. And this will be important later on when I talk about the backward compatibility stuff. Here, by the way, are the 27 different AIS message types. Like I said, my tools deal right now, I think, with 17 or 18 of these. But in any case, what I'm also showing you here is the length of the message. A lot of the messages are exactly 168 bits. Some of the messages are different sizes. Some are variable length. And anyway, I mention this because, again, this will be something that will come up a little bit later on. So here is what my demonstration and capability tool did. First thing, I decided that I can use crypto methods to deal with the problem of message bit integrity. Again, not just individual sentence integrity. If I've got a message that's 1,000 bits, well, a standard message can only be about 168 bits. So a 1,000-bit message is going to need multiple fragments, multiple sentences. The way the checksum works in NMEA right now is there's a checksum on each sentence, but there's no checksum on the message as a whole. There's no timing integrity, so I needed a timestamp. There's no validity and authentication of the sender, so this sounds like public key cryptography is just screaming for that. But I also needed to have backward compatibility. I needed to have a method that I could apply and it wouldn't screw up the system just by being used. So here is my proposed solution. I call this working in protected mode. So I'm a sender and I have a message to send. What my equipment will do is it creates a 16-character, what I call protect string. And the protect string comprises a timestamp and a checksum for the entire payload. That protect string is now encrypted with the sender's private key. And that protection string is now just appended to a normal, the normal content of an NMEA sentence. If you're a receiver and you're operating in protected mode, when you get a message and you detect that there is a protect string, what you do is the first thing is you know the MIMSI of the sender, so you can decrypt it with the sender's public key. That allows you then to recover the timestamp and the checksum. You now compute a checksum, make sure it matches the received checksum, and then you compare the timestamp to the current time to see, well, is this message arriving anywhere near in a reasonable time? Now, as far as public key cryptography is concerned, I decided to use the MIMSI as the key. And the reason being was MIMSIs are different from the IMO number of a vessel. IMO numbers are attached to a vessel. MIMSIs pretty much attached to AIS equipment. And so my idea was, well, if each MIMSI has an assigned private-public key pair, then the AIS device keeps as a closely held secret its private key, and the public key we now have to make somehow available. And we'll talk about that later. So anyway, graphically, here again is the example. I've got my AIS device there on the left. It has some sort of certificate where it has its own private key. It has access to a public key database. When it prepares its outgoing messages, just like it always has, if it's going to be using this so-called protect mode, it creates the protect string, encrypted again with the device's private key. It gets appended to the AIS message, and now it needs to get all of the time slots that it needs to send out the entire message. When it receives an incoming message and it detects the presence of a protect string, it can then, it knows the MIMSI, go get the public key of the sender, and it can then decrypt everything. So my new sentence structure then looks like this. I still have a header. I have content And if the message were small enough, actually, there would be a protect string and then there would be trailer. I actually think I've misdrawn this picture, and I will actually redraw it before it gets out into the wild. The sentence structure doesn't change. The protect string gets added to the content. And if it requires more than one sentence, every sentence looks the same, header, content, trailer. But now the protect string is part of the content. So what does my protect string look like? Well, I mentioned it's a timestamp. I've got a 4-digit year. I've been writing Y2K compliant code since 1973. Anyway, I've got a 4-digit year, month, day, hour, minute, second, all that kind of stuff. It should be clear that you need to have the year. If you don't have the year, if you only had month and day, somebody could do a replay attack 1 year later. And so, like I said, you need to have a complete timestamp. Then I have a checksum. Right now, I've only used an 8-bit exclusive OR checksum because it's the same as that's used for the rest of the NME message. And I figured, well, code reuse. It'd be trivial to put in a CRC8. I'll talk about that in a minute. Anyway, and then I use a 256-bit RSA key to encrypt the timestamp and checksum. Now, I need to slow down here for a second because there really is a reason that I chose this. I chose RSA because when I was looking at the various crypto libraries, the RSA library had a feature that I wasn't finding in any of the other libraries. And when we talk about the library in a minute, I'll tell you what that feature was. The second thing is, when I use a 256-bit key, I generate a 258-bit encrypted string. And as you can see here from the slide, that generates a 26 to 154% protocol overhead, which is awful. But the first time I ran this, when I was doing my experiments and I had a standard RSA key, 2 kilobits, 4 kilobits, I was generating a several thousand-bit encrypted string. Well, if 258 bits is 154% overhead, you can imagine what a 3,000-bit encrypted string was. So I found that 256-bit key was the shortest length key that would encrypt a 16-byte protection string. If I used a 128-bit key, I could only encrypt a 5-byte string. And if I used a 512-bit key, I got a 540-bit protect string. So again, you can see what I was trying to do here was trade off getting the protection of encryption, but at the same time, not overwhelming the protocol with a ton of overhead. So the OpenSSL RSA crypto library has the functions that are listed there that generate key functions, encrypt, decrypt, and all that kind of stuff. But when you use the encrypt function, it not defaulted, it meant you encrypted using the public key. And when you decrypted with the private key. If you wanted message authentication, you had to use the sign function. But a digital signature is huge because they add all sorts of other things that I didn't want to add. What I wanted was merely the feature of a signature that provided me authentication for the sender, but I didn't need everything and all the baggage that came with the signature. So the OpenSSL RSA library also has functions called private encrypt and public decrypt. So that allowed me to encrypt with my private key so that you could decrypt with my public key, and now you would know that I was the real sender. So the only functions out of this crypto library that I use are the generate key, so I can generate a public-private key pair, and private encrypt and public decrypt. Those were, no pun intended, those were the keys to making this all work. Anyway, so here's another example. This is the same message that we had before, but when I do the ping command, everything differs in red. So what I did is I added a switch called the protect switch. So this tells me we're in protected mode. So now what happens when I ran this program or ran this particular message It tells me that the payload is going to be appended with a timestamp and a checksum. So there's the timestamp and the checksum, and it's going to be encrypted with the private key associated with that particular MMSI. Now, if I go back here for a second, I always forget where I put these things. You'd think that after all this time, I would know. I have my public and private key ring. So if I do an ls-la of my public key ring, so here are all the public keys that I have stored in my experimentation. I just needed numbers. And you can probably imagine that I have their private keys in a different key ring. And so there's the private keys. So in any case, when I run the program, that's why it's important that I use a key that I have my public and my private keys for. In any case, so now I run my next program that's going to create my binary string. If you were to go back to the other slide and do a comparison, everything here in black matches what was in example number 1. Everything here in red has been appended. So now when I create this message, it's now 426 bits. It's going to be using 2 fragments. I've decided to use serial number 7. I don't know why 7's so hot, but in any case, you can see down here, here are the 2 sentences that get generated. And when I parse it, again, I have now 2 sentences that need to be parsed. The first sentence now is sentence number 1 of 2, and again, has jazz that we didn't see before. The checksum, works, that's good. And if I go down here, you'll notice that when I parse the message, everything in black is the exact same as it was before, but now we have some additional information. We've got the protected AIS information. So I know my sender is MIMSI. I know that it's authenticated because I compared it to the certificate that I have. There's the timestamp. I compare it to the received timestamp. Well, you can see it got there about 6 months later, but or at least 6 months later. No, I guess, I'm sorry, that's only about 10 days later. I have some examples that are even worse. I just set a threshold saying, I'll tell you how many seconds since the message was sent to when you received it. If it's over 30, I just say it's over 30. You could actually tune that, presumably. But in any case, and then I've got the checksum and it's verified. And again, that's the checksum over the entire message so that I know the message hasn't been screwed with. When I take these 2 sentences and I poke them in to the AggSoft decoder, you will notice I get the same AIS information I got before. And if you recall, the last time we saw this, I wanted you to pay attention to the fact that it was giving me 1 to 26 of 26 entries. That's what the software is telling me now as well. So basically, a type 1 message is 168 bits. The AggSoft software and OpenCPN as well will just say, oh, type 1. Type 1's 168 bits. That's all I'm looking at. And it ignored all the other bits. So this was a way of saying, okay, I can demonstrate I've got some backward compatibility. So what my little project was able to show was this. I can solve the message integrity problem using a checksum. I can solve timing integrity by using a timestamp. I can deal with validity and authentication because I have public key cryptography, and I can use the sender's private key. I can get backward compatibility because it appears that what my experimentation so far is that software and devices will ignore any of the excess bits. Geographic integrity, I didn't even try to work on that because geographic integrity needs to say, I'm a device telling you that I'm at latitude 29 north, 80 degrees longitude west, or longitude 80 west. How do I prove that? And I need to have some other methods to do that. So obviously the big problem is key distribution. This only works if you can figure out how to distribute your public and private key pairs. However, the method that I've described isn't dependent upon your key distribution method. It just observes, yeah, you probably need to have one. So the other nice thing is this. Let's say your device, and it's going to take you 10 seconds to figure out somebody else's or get access to their public key. The fact is, I can accept the message for what it's worth and display it, even though it's taking me 10 seconds to go figure out whether the message is valid or not. So, in my ideal world, I see that you could have messages that you have authenticated and they're in one color. You've got other messages that are being authenticated, they're in another color, and messages that cannot be authenticated, they're in third color. But in any case, there are a variety of ways of doing key distribution. We could use existing public key infrastructure methods, such as, X.509 certificates that we use today with things like SSL. We could use a model, a distributed hierarchical database, such as the DNS. There are currently 1 billion hosts in the DNS, and yet we can get an IP address from a host name in, milliseconds. Well, there's way less than 1 billion assigned MIMSIs. So maybe we could do some sort of database like that. And that probably is the way a lot of the literature suggests we could go. You could do something like PGP's Web of Trust. I will observe that a Web of Trust just isn't scalable. PGP Web of Trust is barely scalable between me and the other, couple hundred people I know that use PGP. But it's certainly not going to be scalable to a very mobile industry, such as maritime. And I mentioned here, there's some other papers that have talked about a number of other things, and in terms of using public key crypto or using some sort of identity-based crypto. There are all sorts of ways of doing this. Most are observing, if they don't want to change the entire AIS protocol, we don't want to have a centralized certificate authority that doles it out to everybody, and you have to go back to that central CA. Most are talking about having some sort of hierarchy. So, for example, and I'm making this up, I haven't talked to anybody about this, certainly in a formal way, but let's say you use the MIMSI. Well, every country has its own maritime authority, and within the MIMSI, there is an identifier that identifies the country. So maybe every country has its own database. So I'm able to look at the MIMSI, I can figure out the country ID, I go to that country ID, it's been pre-programmed in where their database is. All ships are connected to the internet, so they could be able to do that. So anyway, like I said, I'm just sort of making that up as a possible example. There are still open issues with this. What I've described here certainly does not protect me against a bad actor who legitimately has an AIS device that can operate in protected mode. And it also doesn't stop anybody who's got a device from sending purposely false information. Now, presumably, they're only going to be able to do it once because, once they've started to send bad information, everybody's on them. The other thing is backward compatibility means I'm willing to accept messages that can't be authenticated. Well, that means nothing stops a bad actor from just never being authenticated. But if you're differentiating between authenticated messages being authenticated and unauthenticated, so, it puts the bad actor in the unauthenticated space. Anyway, any number of places to go for future research with this. Right now, like I said, I use a checksum that's a bitwise exclusive OR. I could use a CRC8. Hell, I could use a CRC16. Both would be better. Both would keep the protect string well within what a 128-bit key could manage. My current timestamp is 112 bits. I could use a Unix epoch time and not human readable time if I wanted to make it smaller. It turns out if I make it smaller, it still doesn't make the protect string any smaller because I still have to use 128-bit key, 256-bit key rather, sorry. I still end up with a 258-bit protected string. So like I said, I could manipulate that, make it a little bit less human readable. Public sharing, I'm doing, my public key sharing is done via a web of trust. I think at some really official level, you need something way more dynamic and distributed, but this is sort of where I ended doing my research. And I was able to get this to work with almost all message types that I support. I couldn't get it to work with message types that were hugely of variable length. because the problem is one way in which you detect that you've got a protect string, like on a type 1 message, is you see, I'm expecting 168 bits. Anything beyond that, I'm just going to assume is a protect string, particularly if it is whatever 168 plus 258 is. You know, if that's how long the message is, I've got a protect string. If I've got a variable length message, though, I don't know, well, was the message, 1,000 bits, or was the message 650 bits and I've got another 350 bits of protect string out there? You got the idea. Variable length was a little bit difficult unless I could flag that I had a protected string attached, but there's no way within the current protocol to do that. So anyway, I've got some references for further reading if people would like to furtherly read. And obviously, here's my contact information. I've not yet put this software up online, although I'm being incented, not incented, I'm being encouraged to do so, and I probably will. One thing I do have to say, though, is that the tools that I currently have up on my website, I believe are usable by people. If they can read my readme.txt file, they'll be usable. The protected AIS is not quite as ready for prime time, but if people want to play with it, like I said, I will put it up at one of the sites. I've been talking to read out about that. But if you want to ping me earlier, I'm at the point of not minding sharing them. In any case, that's pretty much what I had to say about that. And so let me come back around to here. And I've got, let's see, I've got a number of comments. Hopefully this was going. Okay, they can see my desktop now. Let me see what Readout's got here for me. Yeah, Readout makes the point that I could have used elliptic curve. I'd have to look at elliptic curve. Again, the real, again, I hesitate to use the word key here. The issue that I have is I need a library that will allow me to encrypt with a private key and decrypt with a public key. But other than that, absolutely. And I will freely admit, though, I never got around to looking at the ECC libraries because as soon as I found RSA, I got real excited. But clearly, ECC will give me the same level of protection with a far smaller key. And let me go back to here. And let's see. There's a message here somewhere. I just don't know where it is. Anyway, if there are other questions, absolutely let me know. I will have these slides. There are a couple corrections. I'm embarrassed about this. Believe it or not, you probably will believe it. I was editing this slide deck up until about 15 minutes before the talk. So there are a couple errors that I found as I was going through. I will fix them, and I will get these slides out, and so that they get posted as soon as they can get posted. I'm hearing lots of beeps. Well, I've got another talk coming up in about 5 minutes. And so what I will do is, I'll hang out here for a couple minutes. They'll reset me in a few minutes. And I have a little challenge problem that I want to share with people. It'll only take about 15 or 20 minutes to go through that. But otherwise, thank you all very, very much. And like I said, ping me one way or another if you've got questions or comments. And, my pleasure to be here. And thanks for listening to this. Whoops. Okay, folks, I think we are back. Let me try once again sharing my screen. And once again, I'm going to live dangerously and show the whole thing. So when we were talking about ideas for talks and projects and things like that, one of the things that I just happened to mention, and somebody said, well, this seems like it'd be an interesting, little challenge type of project to do. And I'm going to talk to you about something called AIS point prediction. So here's the general idea. And if I was better at drawing graphics, I could have drawn you some graphics. So I'm going to try going out here to OpenCPN to see what kind of things we got going out here. What I really need, and I probably don't have. Well, actually, I probably do have. But you see these vessels out here. This vessel right here, the Janus, we know is a sailboat. It looks like it's about to come in Ponce Inlet. The Sea King, I don't know anything about the Sea King. It's also a type B. That's too bad, but that's okay. On AIS messages, vessels that are by Code of Federal Regulations required to transmit, Class A type of vessels, so the really big ones have a lot of passengers, have a certain tonnage or horsepower, they're Class A. And a Class A is going to be telling me all the information that's down here. They'll be telling me a speed, course, heading, and turn rate. They'll also be communicating relatively frequently. Class B vessels, the smaller ones, aren't required to transmit. And in fact, in a Class B position report, there's no way to even tell me about a turn rate. So the reason I'm telling you that is so that I can tell you this. My question is, and here's an example of the Louisiana, which was just offshore pretty recently, a tanker offshore Daytona. So if I know a ship's latitude, longitude, speed over ground, course over ground, and turn rate, can I predict where they will be the next time they give me a position report? And in some ways, this sounds like a trivial exercise. I fooled around a little bit with it, not a lot. It's a really interesting exercise. And the idea came to me some time ago, the idea being, I'm at a particular place. And suppose a bad guy spoofs their AIS latitude, longitude of a vessel. And they try to, let's say, knock Louisiana off the air, and now they spoof Bing, Louisiana. Well, suppose their next position report puts me 5 miles away. Well, there's no way that I can move 5 miles in a minute. So my AIS receiver could maybe flash red to say, we just got something that just doesn't seem right. Now, the other thing, by the way, that this AIS message will tell us, this position message, this and other things, is you'll notice that this is also giving me the destination and the ETA when I plan on getting there. So this vessel, which I saw the other day, probably about 4 or 5 days ago, is expected tomorrow morning at 7 in the morning UTC to be in Texas. So it must have, it must have been several days ago. Anyway, so where I'm going with this is this. Again, an AIS type 1, 2, or 3 message is a Class A position report. And the information that matters to me is it's going to give me a latitude. For those of you that are not familiar with the relationship between latitude, longitude, and distance, it is vaguely as follows. 1 degree of latitude is 60 nautical miles. 1 minute of latitude is 1 nautical mile. Longitude is about 1 degree of longitude is about 60 nautical miles at the equator. which is 0 degrees latitude, of course. But for every other, any other latitude, a degree of longitude, the linear distance is going to be some function of the latitude. And think about a globe. And of course, as you get closer and closer to the North Pole, 1 degree of longitude gets to be almost nothing, whereas 1 degree of longitude at the equator is 60 nautical miles. Anyway, I mentioned that later on. Then we're going to have the course in degrees, 0 degrees being true north. And so an actual course will be somewhere between 0 and 359. The speed in knots. A knot, of course, is a nautical mile per hour, which translates to about 1.15 miles per hour. I'm going to have a rate of turn, which is generally expressed in the number of degrees per minute, left or right. And the time between transmission is going to be a function of what is your speed and what is your rate of turn. And it turns out there's a standard for this, and if only the standard matched the reality, life would be a good thing. But here is actually an example and talks about some of the additional issues related to the problem. So I only care about the Class A transponder types, although I'm showing you Class Bs as well. So technically speaking, if you're a Class A vessel, you're at anchor, you just need to transmit every 3 minutes. Now, you may be saying, but I'm at anchor, I'm not moving. Well, again, AIS Class A devices, you might be talking about a vessel that is several hundred meters in length. If it's anchored or moored, the position of the bridge might be actually composing a circle that if that ship were to swing around its anchor in a 360-degree circle, you might be talking about a radius of many hundreds of meters. Well, a nautical mile is about 2,000 yards. So I might, like I said, I might have a pretty big swing radius. In any case, if I'm sailing, not sailing obviously, but underway, between 0 and 14 knots, I'm supposed to be transmitting every 10 seconds. If I am sailing at a speed of 0 to 14 knots and changing course, I need to be transmitting every 3.33 seconds. So that's how you read the chart in terms of transmission rate. What I did is I then translated this and said, well, what's the maximum distance I can travel in that amount of time? Well, if I'm going 14 knots and I'm transmitting every 10 seconds, I'm only going to be traveling 77 yards. That's not very far. And you can sort of see as I progressed here, what I was trying to give was an idea of exactly how far might I be going between transmissions. Now, I mentioned I wish the reality were, match the standard. Sometimes we will see vessels going by that are Class A vessels, and they're pretty big Class A vessels, and like the Louisiana. The Louisiana was going at 15 knots. Well, at 15 knots, even in a straight line, they should be transmitting every 6 seconds. But we had like a minute, that slide that I showed. So in any case, so the distance, or rather the rate between transmissions, is something else we need to take into account. So then I said, well, look, I've got a ship here that's supposed to be a ship, and it's at some latitude and longitude, which I'm calling lat 0 and long 0. I know my course over ground. I know my rate of turn. And so the question is, all right, well, I've got a triangle in here. I've got some angle theta. Now, this may or may not be the right approach to go, by the way, but I've got some angle theta. And so at some t time later on, I've got my new latitude and longitude, lat 1 and long 1. And so I will observe that I can figure out the radius of this circle because it's going to be related to the speed over ground and the rate of turn. I can figure out the distance that I've traveled, that circular distance, that the arc, if you will. That's going to be somehow related to the velocity times the time between the transmissions, the actual time. And then I've got this delta x and delta y. Well, delta x is going to be a function of the angle of the circle, the speed over ground, and the time, which, as we'll my delta y. But then my actual change in latitude and longitude has got to be a function of the course plus theta, meaning that if I was just going due north or do anything, it'd be easy. But as we start to change off of 0 degrees, we start to see, some complications. Because again, a degree of latitude is the same everywhere in terms of linear length, but the linear length of a degree of longitude is not going to be the same. So, like I said, we have, that issue to deal with. So again, my targets that I'm going for is if there's no rotation of the ship and the ship is moving in a straight line, well, that's almost easy to do. If the rate of turn is not 0, my ship is turning. And so then the other thing I was thinking of is not only how well can I predict my next point, but we just had a tropical storm down here last week. Went up the East Coast, and so we always look at the National Hurricane Center, and they give us this cone of certainty. For so that if my next point is in the box, do I claim victory? And am I looking for, a really small box, or how big will I let my box be? If I'm going in a straight line, they really are sort of boxes. If my rate of turn isn't 0, then the boxes actually become a cone. Am I anywhere in the right range at all? So, like I said, in terms of a problem, I was just thinking that this sounds like an interesting problem to tinker with. And there's all sorts of places to look at historical information. What you need to work on, though, if you get historical information, and I could even provide you some, is you need type 1, type 2, or type 3 position reports from the same vessel. And the type 1, again, because you need rate of turn. Now, I mentioned something about the length of a degree of latitude and longitude. So again, the length of a degree of latitude in meters, there's a formula that I know is used at a number of the government sites. It was actually easy to find the formula because they have these pages where they have like a JavaScript, and you can put in what your latitude is. It will tell you the length of a degree of latitude in meters. Well, of course, if you right click and look at the page source, you can see their formula. But it's been used a lot, and I've seen it documented in a few places. In any case, the length of a degree of longitude, again, you will also notice is a function of the latitude. The length of a degree of latitude and longitude, here's a table that I produced largely from those formulas. And you will notice that a degree of latitude, in terms of nautical miles, it almost doesn't matter where you are. It's about 60 miles, 60 nautical miles to a degree. If you look at a degree of longitude, the number of nautical miles, again, at the equator, it's about 60. And then as you go towards the poles, it increasingly gets smaller and smaller, and then rapidly gets smaller once you get above about 45 degrees, either north or south, and that actually makes sense until, of course, you get to the pole, and then the degree of longitude is 0 nautical miles. And again, I've given you some websites where they have more information about this, and that more or less was the challenge. And as I said, I think it's sort of an interesting problem, and for a few people. I don't know where we sort of go from there. Like I said, I talked to Reed out about this, and I think he talked to a couple of other people. interesting problem. I think what we're looking for is maybe to have some intermediate solutions at some point in the next year. Maybe revisit this at Have to See 3.0 next year. And anyway, so that's where I am. So questions, comments? Let me go back up here. No, I'm no longer at Hack the Sea Village. So I'll sit here for a couple of minutes while we go into Q&A. Well, where I'm sitting is a lot of dead air. I'm going to hang out for another few minutes. Clearly, if anybody's got anything, let me know. And again, contact me by email or whatever seems to work. And let me know if you have questions and how we might go forward with this. And other than that, I thank everybody for attending whatever talks of mine you attended. I had a blast. Hope you had a blast. And go from there.